Good morning, everybody. I'm going to talk some introductory information about on lightning from an electromagnetic point of view. So we know that it can have some other physical aspects, but what we are going to focus in this presentation is only the electromagnetic point of view. Let's have a look at the outline of my presentation. First, we will have an introduction, what's lightning, the lightning discharge, and then I will review instrumented powers and artificially initiated lightning, and I will review also lightning electromagnetic field signature, the most important signatures for electromagnetic engineers, and also I will finalize my presentation with concluding remarks. Okay. Lightning discharge presents one of the largest sources of electromagnetic disturbances which can affect a wide range of electrical and electronic systems. Essentially, to study lightning, we should do some instrumentation, some measurements. Data on lightning electromagnetic fields can be obtained essentially using one of the three of these techniques. First, natural lightning, which gives us EM field characterization of lightning from distances of 1 kilometer and beyond up to 200 kilometers. So mainly we can say that from moderate distance up to far distance. And data on the data that we can obtain from lightning solid structures is lightning current, and in some cases electromagnetic fields. Since with instrumented towers we can measure the current that is flowing through the tower, and we can characterize that current. And also the third case is artificially initiated lightning, which gives lightning current and electromagnetic fields, but with the difference that we can measure electromagnetic fields of lightning from distances down to few centimeters. So you see the three methods of measurement of lightning cover almost all the cases related to electromagnetic field calculation and measurement of lightning. So in this presentation, we summarize the main process of lightning relevant to EMC, and we review measurements of electric and magnetic fields produced by negative cloud-to-ground lightning discharge. What is lightning discharge? Lightning discharge, as defined many years ago, is a transient high current electric discharge whose path length is measured in the order of kilometers, 5 kilometers, 10 kilometers. So it's a pretty long current distribution, and it is the most common sources of lightning, which is for lightning discharge. The most common source are the charged thunderstorms. The two charge centers are normally separated in the thunderstorms, and these thunderstorm clouds are called cumulonimbus. So this is the main sources of lightning discharge worldwide. If we take a look at the typical lightning thunderstorm, lightning cloud, it consists of three different charge regions. One main negative charge region, which is usually occupies the lower part of the thundercloud, and the other positive charge region, the upper part, and we have a very small portion of positive charge. This is the in the vertical axis you will see the altitude of the that the thundercloud occupies, and here the temperature regions. And a typical electromagnetic field, electric field at the ground level, Velskar 1, is shown in this axis on red scale. As you see, it measures on some tens of kilowatts. This is a very preliminary data on lightning thunderclouds. There are essentially three types of lightning discharge. One is intracloud, which is a lightning discharge between two separated charge centers in the cloud, and the other is intracloud, between two separated charge regions between the two adjacent thunderclouds, and cloud to ground, which is the lightning discharge between cloud and the ground. So what we are concerning in this presentation is cloud to ground lightning discharge. And for this type of lightning discharge, we have essentially four types. Downward negative, which lowers negative charge to the ground. And upward negative, which again lowers negative charge, but is initiated by upward leaders and is initiated by tall structures. Downward positive lowers positive charge to the ground, and upward positive, again positive charge are lower to the ground, but is initiated by upward negative leaders, again initiated by tall structures. So about 90% or more of the global close to ground lightning is due to downward negative, and 10% or less is of close to ground positive downward negative discharge. So we have 90% downward negative, less than 10% downward positive, and the rest, upward negative and upward positive, occur only from tall objects more than 100 meters in height, and or from objects of moderate height located on mountain regions. So due to the importance of that downward negative, we just review in this presentation this type of lightning, and we will pay more attention on this. Let's have a look on the process of downward negative lightning. What is happening inside? We have charged thunderclouds, positive at the upper part and negative at the lower part. There we will have some preliminary breakdown inside the thundercloud, and the charges are initiated to travel downward to step leaders. It's called a step leader because it moves downward in a step fashion. It is not in continuous way, and it travels downward toward the ground. When it approaches the ground, this negatively charged line, when approach the ground, we will have upward connecting leaders that are trying to join this negatively charged region. So after some force, we will have attachment process, and then after that we will have the first return stroke. This is one of the most important parts of lightning discharge because it's a high amplitude currents and with considerably smaller rise times. So after first return stroke, we will have again the dart leaders. We call this dart leader because it is propagating in a continuous way, and the reason for dart that the dart leader is continuous and the step leader is in a step way is that dart leader is propagating inside the channel originally developed by the step leader, and also by the first return stroke by step leader is traveling in a virgin air. And after the dart leader, we will have subsequent return strokes, which again we call it always subsequent because in a lightning flash we can have up to 10 or 20 of return strokes. The first one is always called first return stroke, and the second one and the third one and so on are subsequent return strokes. And if we want to take a look on what's happening from the current point of view, because what is really important for the lightning, if we want to consider, for example, direct effects or indirect effects, is one of the most important parts are the currents. If we take a look at the dart leader moves at the speed of about 1/10 of the speed of light, and essentially we can neglect the current related to this because before that we had some step leader, first return stroke. The return stroke essentially is a current that is an impulsive current wave shape, and it propagates from the ground upward toward the thundercloud. And the speed is from 1/3 to 1/2 of the speed of light. After that, we will have a continuing current. You see the amplitude of the continuing current is not comparable to that of first and subsequent return stroke, but the duration is really considerable. And after that, we will have some M components. We call it these high rise time and low amplitude impulsive wave shapes, which are superimposed to the general lightning current waveform. Continuing currents are essentially responsible for most serious damage of lightning associated with thermal effects, such as burn holes owing to the large charge transfers, because although they are low amplitude, but the duration of the current is in the order of milliseconds. The duration of the first return stroke is in the order of some microseconds, hundreds of microseconds. And the rise time, I will show you on the later that the rise time of the first return stroke is on the order of microseconds. And the highest directly measured lightning currents near 300 kiloamps, and the largest charge transfer, hundreds of coulombs or more, are due to positive lightning. So I will just, again, review. We had some 10% or less positive lightning, 90% or more negative lightning, but positive lightnings are characterized by higher current waveforms, higher amplitude currents, and higher rise times, and negative lightning by lower rise times, lower amplitudes. By the way, they are more frequent than positive lightning. Here is a video of lightning, I think, done by Tom Warner. High-speed video, 7,200 images per second of a negative cloud to ground flash captured on August 15 of 2008 near Rapid City, South Dakota. So just to see what's happening, this is a vehicle that is moving at the speed of 100 kilometers per hour, and this is just a wave shape of the line of the return stroke. You see we have some branching here, and it hit the ground. So let's move to the we'll have the next one. Usually, we want to characterize first and subsequent return stroke currents from a fine structure. We usually have some leader path shape. We call it L, and we have some slow front and fast transition called R. So we have here some orders of microseconds. This is typically for, I think, first return strokes, and you see the amplitude is 5, the division of the horizontal axis is 5 microseconds per division, and this is the, excuse me, I call the current. This is the electric field, and we have some impulsive wave shapes on the main peak, which is called alpha A and B C component. And for the subsequent return stroke, you see we have lower amplitude but lower rise times. Again, we have the same impulsive waveform before the initiation of the field, leader pulses and front pulses, and again we have the rapid transition. You see in the first return stroke we had some the amplitude of secondary peaks are larger compared to the amplitude of the first peak, but in the subsequent return stroke the current is a little bit filtered. I mean, the secondary peaks in the subsequent return stroke are smaller compared to the first return stroke, as I mentioned earlier, because the channel is already shaped and we have a smooth transition of the charge to the ground. Here is the one of the most important electric and magnetic field measured from first and subsequent return strokes. The solid lines are due to first return stroke, and the dashed line are due to subsequent return stroke. As you see, this is the vertical electric field at a distance of 1 kilometer from the channel base. So we had the lightning; it propagated outward to the cloud. This is the first and subsequent return stroke portion, and this is the electric field and the azimuthal magnetic field measured at ground level at a distance of 1 kilometer from the channel base. We call the path of propagation of lightning as the lightning channel, and the attachment point to the ground, we call it channel base. You see the electric field at a distance of 1 kilometer is characterized by an increasing ramp, and the magnetic field by a first peak followed by a hump, this second peak. And at a distance of 2 kilometers, the ramping phenomenon is decreased, and also the hump also is degraded. And at a distance of 5 kilometers, we see here that we have a first peak in the electric field, and followed by a minimum and also an increasing ramp. And also for the magnetic field, we have a first peak and also by minimum followed and also by hump. The same phenomenon is almost observed at a distance of 10 kilometers and 15 kilometers, but at a distance of 50 kilometers and 200 kilometers, as you see, the wave shapes of the vertical electric field and azimuthal magnetic field are characterized by a first peak. There is no increasing ramp. We have a zero crossing, and we have a double priority waveform of the electric field, and also the same phenomenon for the azimuthal magnetic field. And as the distance increases, the two wave shapes are becoming similar. This is what we have expected, because at a distance far enough from the lightning channel or from the electromagnetic source, we should have almost TM wave phenomenon. So the ratio of the vertical electric field to azimuthal magnetic field should be essentially the free space impedance. And this zero crossing and also the hump, the first peak, are usually used by lightning locating systems to characterize the lightning, and in some cases even locate the lightning incidence. So what we talked here up to now was about the natural lightning, the current features, and also the electromagnetic field waveforms. Let's move to the instrumental towers. Tall towers are often struck by lightning due to their height. Tall towers are means to record lightning currents and associated electromagnetic fields because we can instrument them. We can put some sensors to measure the current. Here you see one of the most representative of the one of the most important measurements carried out by Berger in Switzerland, in Mont San Salvatore, in Swiss Italian part, and the you see the branches, everything else. The measurement of Berger et al. In 1975 are one of the most references that is used currently by lightning researchers. And here, as I talked earlier, we can characterize the currents. As you see, the first figure is due to first return stroke, and the second figure is due to subsequent return stroke. And the two scales are shown, the solid line on A and on a larger time scale compared to a dashed line on a smaller time scale. As you can see here, the first and subsequent return strokes are characterized by the first one by higher rise times, but the second one by lower rise times. So if we want to see the effects of first and subsequent return stroke, we can pay attention to the rise times and also to the peaks. Here is one of the, again, most important characterizations of lightning currents due to Berger et al. And as I mentioned earlier, it is one of the most important sources. For example, if we have first return stroke and subsequent return stroke peak currents, on the average, first return stroke peak current on the order of 30 kiloamps and subsequent one 12 kiloamps. So we can say that first return stroke currents are 3 times larger than those of subsequent return one. And if we take a look at the front duration or rise time for first return stroke is on average 5.5 on the measurement of Berger, and subsequent return stroke 1.1. You see, first return stroke have larger peaks and larger rise times. Subsequent return stroke smaller peaks, smaller rise times. And one of the most important features is the maximum rate of rise, or di over dt. For first return stroke is 12, and for subsequent return stroke is 14. So if you want to see the radiation effect, which is usually measured by the derivative of the current over time, we see that subsequent return stroke can be more dangerous than first return stroke ones. And if we are worried about the direct effect charge transfer, you see for the first return stroke is 5.2 on average, and for subsequent return stroke on the order of 1 coulombs. And as I mentioned earlier, if we are worrying about the direct effects, which are usually done by charge transfers, we should pay attention to first return strokes and also to continuing currents, because although they have lower amplitudes, they are longer in duration than the other phenomenon inside the lightning. So let's move to the other measurements carried out to characterize lightning. An instrumental tower, piezometric tower in Germany, Toronto CN Tower in Canada, and also Sentis Tower in Switzerland. We have just started instrumenting it, and we have also measured some currents on this tower, you see the problem is becoming more important because as we go forward, we need to better characterize lightning currents. This is a transient process along the tower. You know, when the tower is struck by lightning, one of the most important phenomenon is how to characterize the transient phenomenon inside the tower, because the tower is struck by lightning at the top and the current travels downward and upward along the tower. As you see here, the current at the height of 533 meters is about 80 kiloampere, one of the measured waveforms. But at the height of 272 is around 10 kiloamps, and at the height of 47 or nearly the tower base is 22 kiloamps. So we can see that the current at tower base is doubled compared to the current at the tower top. And this is due to the reflection at the ground level. So another measurement is here due to the Toronto CN tower. We have two measurements set up at 509 meters, 474 meters. You see the waveforms of the two currents. Here we see the reflection considerably compared to the previous that I have shown, and this is again the ground reflection. Another current waveform is the return stroke current measured along the Peisenberg Tower in Germany, and you see again the doubling, almost doubling of the current measured at the tower bottom compared to tower top. The last set of measurements is the one that we are doing at the Swiss Federal Institute of Technology, EPFL, in St. Tower in Switzerland. Essentially, we have this tower is one of the towers most struck by lightning in Switzerland. We have two Rogowski coils here at the height of 67 and 20 meters, which measure essentially the lightning currents. And also we have BDOT sensors, which again measure the magnetic field but can be transferred to the lightning current. And these are transferred to the control room and so on. And here we have what we are really doing inside this measurement system. So just for review, and this is the typical waveform measured at the tower top and tower bottom. As you see, here are the fine features observed due to the reflection of the current along the tower. And this is the first flash that we have measured at St. Tower in Switzerland. So let's move to the triggered lightning, the third case of lightning measurement system. In the triggered lightning, we have a rocket that is moving at a speed of about 200 meters per second upward toward the thundercloud, toward the charged thundercloud. And at the height of about 300 meters, this rocket initiates upward positive leaders. So these leaders move at a speed of 10 power of 5 meters per second toward the thundercloud. And after that, we will have this third phenomenon, which is usually the leader is approaching the thundercloud, and after that we will have some currents. We call it initial continuing current. This is different from the continuing current that we had after the first return stroke in the natural lightning. Then we will have some no current interval, and from this step ahead, we had leader return stroke sequences that are very similar to subsequent return strokes in natural lightning. So these three phenomena can be considered equivalent to the first return stroke and the first step leader of the natural lightning, and the rest are, as I mentioned earlier, similar to the subsequent return strokes. And again, the subsequent return stroke travels with the speed of about 1/3 of the speed of light to 1/2. The wire in the triggered lightning, because we had a rocket that is connected to the wire, and it offers the wire toward the thundercloud, plays the role of the grounded object that rapidly extends and then replaced by the plasma channel of the upward leader. And this is a flash that is measured in 1997 at ICLRT in Camp Landing, Florida. To compare the two current waveforms related to natural and subsequent, triggered return stroke, we can, as I mentioned earlier, we have some sort of charge transfer in the first return stroke, amplitude on the order of 100 kiloamps, charge transfer of 5 coulomb, and the initial stage of the triggered lightning is characterized by initial continuous current, some 30 coulombs of charge are transferred to the ground, and then we will have this subsequent return stroke for the two phenomenon and also the subsidiary peaks observed, which we can call it this one as the continuing current, as also here. You see, this the phenomenon are almost the same after the initiation of the first subsequent return stroke. So, if it works here, we see initiation of a triggered lightning, and this was the return stroke. Okay, and this one was measured at a distance very close to the lightning channel, to the triggering equipment, and this one is measured at a distance 500 meters away from the triggering system. Yes. So, as you saw, this one was the wire that vaporized after the initiation of the first return stroke. So, as I mentioned earlier, the advantage of this system is that we can measure lightning electromagnetic fields at a distance of up to few centimeters. Very important that we cannot do by other techniques like natural lightning, and also we can measure the current in this case. As we go closer to the lightning incidence point, then we see such a waveform. We call it asymmetrical V-shaped electromagnetic waveform. This is for electric field, and this decreasing part is due to the field change due to the downward leader stage, and E-field change due to the return stroke is characterized by this, the other part of the V shape. As you see, it is asymmetrical, and the bottom of V is the transition from the leader to return stroke sequences. So why it is important? Because at a distance very close to the lightning here, for example, 500 meters, the electric field due to the leader is also becoming important, because as we don't have such effect at far field due to the lower speed of the leader, but at the near field, due to the closeness to the lightning channel, the electromagnetic field due to the electric field due to the leader becomes very important, and we characterize it. And this slide is adapted from a paper by Rubinstein et al. In 1995 that our lab also contributed on this. And as you see, the width of the V is typically at the order of 100 microseconds at a distance of 500 meters. And at a distance of 13 meters, the width of the V is on the order of few microseconds. But we see the same asymmetrical waveform for the electric field. So let's move to the summary. I've shown in this presentation that electric and magnetic field signatures of negative close-to-ground lightning at distances ranging from a few meters to 200 kilometers were reviewed and discussed, and we see that we can characterize these fields by measuring electromagnetic fields due to natural lightning. The most significant radiation is associated with the return stroke of the lightning discharge because of the impulsive waveform, because the high rate of rise of the first and subsequent return strokes. But again, the most important is the subsequent return strokes. However, at a distance that close as few tens of meters, the electric field change associated with downward leader becomes very significant due to closeness to the lightning incidence. And magnitudes and wave shapes of the electromagnetic fields vary considerably as a function of distance, as we see for natural lightning. At very close distance, within 100 meters or so, the leader return stroke electric field change is characterized by an asymmetrical V shape, the bottom of V being associated with the start of the return stroke. And at distance of about 1 to 10 kilometers, the return stroke electric field is characterized by a first peak, followed by an increasing ramp, and a magnetic field is characterized by an initial peak followed by a hump. As I mentioned, these features are used to characterize and to locate lightning incidents in lightning location systems like NLDN in the United States and also in Europe. At far distances, 50 kilometers and beyond, the electric field and magnetic field are characterized by similar bipolar waveforms, a zero crossing, and also the ratio of the two can be equivalent to the free space impedance. And at 100 kilometers, typically the E field peak is in the order of few volts per meter. For shorter distances, the radiation peak can be estimated using a 1/d dependence from the electric field at a distance of 100 kilometers. Thank you.
Yeah, thank you very much, Hamid, for this presentation. Are there any questions? Okay. No. Thank you. Thank you again. So next.